Thank you, and thanks for the invitation to this great meeting and for the opportunity to escape winter in Boston. So, exactly 24 hours ago, we were introduced to distinguished representations, and this is a continuation, or maybe a different case. So let me just remind you the definition. A representation of a group G is distinguished by a pair H chi if the space of intertwiners is non-zero of H intertwiners, and here chi is a character of H, which is a subgroup of G. So, for example, if G is a GLN, say, over a group, and our subgroup H, I'll denote it by N. N is the upper triangular unipotent subgroup in G, and we choose any non-trivial character of the additive group, then we can define the standard non-degenerate character of the unipotent group, psi of the sum of elements above the main diagonal. And to be distinguished by this pair is to be generic in the sense described yesterday in Sarah Dishel's lecture. So this space is the space of Whittaker functionals. All right, so we've already heard the generic representations are nice, so distinguished representations are nice. And the case that I want to focus on today is so my representations are always C-valued. SPN distinguished representations of GL2N, where F is a p-adic field. I guess smooth representations, in the sense was described in Seychelle's lecture. So, as pointed out yesterday, distinction is somehow captured by some subgroup that is related to G and H. And in this case, one can see geometrically this other group that captures distinction is the group GLN. So the geometric picture is that there is a natural bijection from, and this is over any field, conjugacy classes in GLN and the double cosets in GL2N by SPN. So just this map defines a bijection, and for various reasons, this similarity between these spaces indicates that there should be a lifting of representations from GLN to GL2N that captures the distinguished representations in this context. And what is known, if pi is any representation of GL2N of a local field, then the parabolically induced representation so I'm using the Bernstein-Zelevinsky product notation for parabolic induction. So this is a if pi is a representation of GLN, then this induced representation is a representation of GL2N, and it is SPN distinguished. So in a way, this explains the transfer, but these representations are not irreducible. So we're not constructing the example of irreducibles that are distinguished in this way. So if, for example, pi originally was a tempered representation, then this representation is a Langlands quotient, and this Langlands quotient will be distinguished as well. So the lifting is a map from pi to what is sometimes denoted as the isobaric sum of these two representations. So it has an analog, of course, in the global context, where this lifts to residues of Eisenstein series. In the local context, it's just the Langlands quotient. And at least as far as tempered spectrum goes, this should capture the whole picture. Tempered representations of GLNF lift to tempered representations of the symmetric space, and it should be all tempered distinguished representations. So this is compatible with the conjectures of Venketesh and Sekalaridis in a much more general setting. And what I'd like to describe is, so I've been looking at this case for over 10 years, and 10 years ago, and then there are some recent observations that I would like to discuss today. So what would be a possible approach to obtain all distinguished irreducible representations? Well, one could use one of the classifications, so possible approach for distinguished Morse dual is to first, so one could use the Langlands classification and first try to study distinguished standard modules. So classify distinguished standard modules. And then if you have a irreducible representation, well, you realize it as the Langlands quotient of its standard module. And then there is the projection of lambda to pi defines an embedding of spaces of invariant linear forms. So, I guess in this case, and which means in particular that distinction of the standard model is a necessary condition for distinction of pi, but then it is a much more delicate question to find the image of this embedding, and to find whether it's actually 0 or not. So which, if a standard module is distinguished, which of its component is the distinguished component? And that's a question that, in general, we don't know how to answer. So what do we know about the first question? We don't have a complete answer to the first question, but we have some idea of what is going on. So let me describe what is known in this situation. So if we're taking a standard module and write it down in terms of its square integrable data. So here, delta I are essentially square integrable representations of smaller GLs, and the exponents are in decreasing order. Then, first of all, so we assume that all the square integrable data are different from one another. So that is, of course, a restrictive assumption. And there exists an involution with no fixed points W on T, on a set of T elements, such that delta of Wi is absolute value of the determinant times delta of I whenever Wi is less than I. So in some sense, this addition says that the square integrable data is compatible with this picture. So if this is the case, then lambda is SPN distinguished. So this is I should have put it here. This is a result in a paper from 2017 with Arnab Mitra and Eitan Sayag. And I later observed that the converse of this statement is true in general for standard modules. So this is really merely an observation that so actually I'm confused about it. Yeah, I'm confused about the direction. So let me recap. So no assumption here. So if there exists an involution with no fixed points such that the data here satisfies this property here of the lifting, that square integrable data comes in pairs like this, then lambda is SP distinguished. So this is a sufficient condition for general standard modules. And in the paper with Mitra and Sayag, under the assumption that the square integrable data has no repetitions, we prove the converse, which is that if lambda is SPN distinguished, then the data, the score integrable data, is of the form that we expect it to be. So it is reasonable to expect that this is the characterization for general standard modules. But so in our paper, we reduced the general case to a purely combinatorial statement about segments of integers. But we don't seem to have a feeling for this, the translated statement, which is in terms of in completely elementary terms, but still we don't have a sense of evaluating whether it should be true or not. And I guess a good programmer can probably test it for many big enough data cases to get a better feeling. Okay, so maybe the Langland's classification approach does not give us a complete answer to the first case. And we did a little better with the Zelevinsky classification. So I would like to describe that later, but in some sense, the results of it concerning the Zelevinsky classification aspect are nicer put in a more general context where we don't only consider symplectic distinction, but also other periods. So let me recall the family of periods that I'd like to consider. They are referred to. They were introduced by Kaliechko. So we're basically looking at the following subgroups. So if we have any decomposition of n as 2k plus r, we write hr for the subgroup spk here, anything here, so and nr. And we extend the character, the generic character on nr, we trivially extend it to this subgroup. So consider theta r of hx0u is theta r of u. Okay. And we want to study distinction with respect to this subgroup and this character for any r. So r has to be of the same parity as n for these subgroups. So you can think of, so if r equals 0, this is a symplectic case. And if r equals n, this is the Whittaker case. And this is kind of an interpolation between these two cases. So let me just introduce this notation of the Kaliechko multiplicity of a representation. So this will be the sum of dimensions of the spaces of periods of the representation with respect to all Kaliechko models. So R here is between 0 and n and in the same parity as n. Okay, so before describing some results for p-adic groups in this context, let me recall a really beautiful result about what happens in the finite field case. So this is a theorem that was, I guess, first stated by Kaliechko in 1984, but maybe the first complete proof was given by Inglis and Saxel. In 1991, and it says that for any reducible representation of GLN over a finite field, the Kaliechko multiplicity is exactly 1. So sorry? Oh, yeah, maybe I should call it differently. Yeah, okay. Sorry, thanks. Yeah. So what this basically says is that if you apply Frobenius reciprocity and you look at the sum of all these induced representations, they actually realize all irreducible representations of GLN over a finite field exactly once. So you get to realize every irreducible representation uniquely in a space of functions. And this is what Gelfand meant by the notion of a model for a group. So it's a very nice picture over a finite field. And the first to consider, so I'll go back to the p-adic case now. And the first to consider the case of a p-adic field were Hoymos and Rallis. And they had several results. In particular, they proved the multiplicity one for the symplectic periods, but they also observed that this picture cannot completely be satisfied. So as long as n is greater or equal to 3, there exists pi irreducible representation of GLN over a p-adic field with no Kaliachko model. So for GL2, this family of models, there are just two of them. There is the Whittaker functional for R equal 2, and for R equals 0, it's the symplectic functional, which is just SL2. Now, an SL2 distinguished representation is just one-dimensional. And all the other representations of GL2, they are generic, so they have the Whittaker model. But as long as, if you go to GL3 or further, then you can find representations that don't have Kaliachko model. So in 2008, we proved that part of this can still be saved. So for every pi irreducible the Kaliachko multiplicity is at most 1. So any representation can be embedded to at most one Kaliachko model, and it can be embedded uniquely. And furthermore, if pi is unitary, then you actually get a Kaliachko model, and we prescribe exactly which one in terms of the Tadic classification. So I should say at the time, the proof of existence for unitary representations was a global one. We've used periods of Eisenstein series. But now, the work I mentioned together with Mitra and Sayag actually provides a more general statement about existence of Kaliachko models, not just for unitary, but for a larger family of representations. And it's a purely local proof. So this fact now, so these entire results are now purely local. Okay, but this was a while ago. And as I mentioned, I'm heading towards result in terms of the Levinsky classification. So I will very briefly recall what is Levinsky's classification for irreducible representations of GLN. and in a way will formulate a result that works more analogically with the finite field case. Okay, so first of all, I'll introduce the notion of segments, which again we've heard about yesterday. So a segment will be a set, I'll denote like this. So it's a set of cuspidal representations. It's the twists by powers a plus I of a given cuspidal representation rho, where I is between 0 and k. And so in my notation, I will always fix the data so that rho is a unitary cuspidal representation of some GLD, and A can be any real number, and K is a non-negative integer. Okay, and the segment representation so Z of delta is the Langlands quotient of the representation induced from the set of representations in the segment. So absolute value to the A plus K rho up to absolute value of rho. So Langlands quotient of, sorry. And the Levinsky classification is a construction of all irreducible representations in terms of multisets of segments. So what replaces the standard modules in the Levinsky classification is, so given a collection of multisets where we may have repetitions. So, sorry, a collection of segments. We order them in such a way that the starting point of every segment is in an increasing order, and the Levinsky module is defined to be the product of the Levinsky segment representations put in. Now, there are many orders that satisfy this, but the Levinsky module is going to be independent of such an order that is chosen. So this representation has a unique irreducible quotient, and it is denoted by Z of the multiset. And the classification is the statement that this map from multisets to irreducible representation is a bijection from multisets of segments to the union of irreducible representations of GLN for any n. So the one recent observation is that on the level of Zelvinsky modules, we have a result which is completely analogous to the finite field case. So for every multiset M, the Kaliachko multiplicity of the Zelvinsky module is exactly 1. So there is a unique Kaliachko model and a unique embedding to it, even though these representations are in general not irreducible representations. Okay. So, I mean, for a long while we're wondering about the difference between the two cases, and at least there is a formulation for which there is an analogous result to the finite field case. But it also gives a recipe to exactly which Kaliachko model in terms of the multiset, and I can give you the recipe as follows. So for this I need to define an invariant of a multiset. So first I will define an invariant of a segment. So the odd part of a segment, let me write the segment to be of length k instead of k plus 1 as I wrote it earlier. So the odd part of a segment of length k is 0 if k is even, and it is d if k is odd. And remember, d is such that rho is a representation of GLD. Okay. So the odd part of a multiset is defined to be the sum over all segments in the multiset with multiplicity of the odd part of the segment. And the result is that, in fact, this space is 0 as long as R is not the odd part of M, and it is one-dimensional exactly when R is this invariant of the multiset. What is D? Yeah, so rho is a representation of GLD. Where is my definition of a segment? Okay, so it's the D for which rho is a representation of GLD. Okay, so this segment is related to GL of D times K. Okay, and if your segment is odd, then the odd part is D. Okay, so what are the ingredients? So the key ingredient is really this result for symplectic period, and that's already in the paper with Mitra and Sayag. And that's the result at home SP is one-dimensional if all segments in M are even, or in other words, the odd part equals 0, and it is 0 if there is a segment which is even, which is odd. Okay, so this is a result that comes from a careful analysis of geometric lemma. And for the second ingredient, for a general Kaliachko model, remember that this space, so I should have, maybe I should recall this. So let's look at the Kaliachko subgroup. I guess I erased this. I wanted to keep it on the board, so let me write it down on the other side. So the subgroup HR was SPK and NR, and then we had theta R, which was really the trivial character everywhere except here there's a theta R. And if you just focus on the subgroup coming from these blocks, you will get a period which is invariant just by, or equivariant with respect to the character in this subgroup, can be described in terms of a Jacquet module of a subgroup. And so this Jacquet module, with respect to this subgroup and the character theta R of a representation, is exactly what is called the Bernstein-Zelevinsky derivative, the rth derivative of pi, and it is a representation of GL, well, 2K in this case. So if you go back, any linear functional which is equivariant with respect to the Kaliachko subgroup has to factor through the rth derivative. And this space is really SPK of the rth derivative of zeta m. So this observation reduces us to two things. One is the first problem, right? Studying symplectic distinction, but it's symplectic distinction of an rth derivative of a Zelevinsky module. So we need to know something about derivatives of Zelevinsky modules. And it's not hard to observe that, well, zeta m R itself it's not a single Zelevinsky module, but is glued together. So that means it has a decomposition series with components which are Zelevinsky modules for some other multisets. And there is only one multiset that will appear in this decomposition, which all its segments will be of even length, and that can only happen if you take the derivative with respect to exactly the odd part. And so information about the way the rth derivative decomposes reduces this problem to the first part. Okay, so in some sense, this in the language of Zelevinsky modules, this finishes the first part of the project. And it also tells us that so this invariant, the odd part, gives a necessary condition for distinction of irreducible representation. Let me just add this part of the talk with a corollary that if pi is any irreducible representation of GLN, which is HR theta R distinguished, so it has the this Kaliachko period, then we must have that R is the odd part of M. Because again, distinction of a quotient implies distinction of the Zelevinsky module. Okay, So for the rest of the talk, I want to address a problem that has to do with restricting representations that are SP distinguished to SLN, to SL2N, and trying to identify which SL2N component is the distinguished one. And there is a nice conjecture formulated by Sarah Dishol and Dipendra Prasad, and I'd like to describe it. So, for any irreducible representation of GLN, the restriction to SLN is multiplicity free. So and of finite length. So if you have any situation where H is a subgroup of SLN, such that you have multiplicity 1 for the periods this means that so there is an age-invariant linear form on the space of pi, and if H is a subgroup of SLN, it can only be non-zero on one of the SL components. Right? If two of them would have an age-invariant linear form, this would give a two-dimensional linear form here. So that means that there is a unique I such that pi I is H chi distinguished, and I'm going to denote this distinguished component as pi H chi. Okay, so there exists a unique I such that pi I is H chi distinguished, and I'll denote it like this. So I want to consider this in two examples. So if in the case where so for every pi an irreducible representation of GLN, the Levinsky associated a partition alpha pi of n such that the dimension of these periods are 1, but theta alpha now in gen is the following character of the upper triangular unipotent subgroup. So it's given by a sum over all i's, so psi ui I plus 1, where you skip the partial sums n1, n1 plus n2, and so on. So basically, you can think of theta alpha as the generic character in each block of size the component of the partition, and outside you apply the trivial character. Okay. And actually the prescription is by the Bernstein-Zelevinsky derivatives. So so the first component n1 is maximal such that pi n1 is not 0, and then this representation pi n1 is called the highest derivative of pi, and n1 is called the level of pi, or the level of non-degeneracy. And then n2 is defined to be the level of the highest derivative of pi, and so on. It is a recursive definition of consecutive highest derivatives applied to pi. And in fact, it follows from a later work of Moglon and Valls-Pouget that this is actually the maximal unipotent orbit of the representation. So in this case, I would like to call the distinguished component of the restriction of pi to SLN the Zelevinsky component, and I'll denote it by pi d. Okay, so this is the Levinsky component of pi restricted to SLN. And the second example I want to consider is that pi is an SPN distinguished irreducible representation of GL2n. And in this case, I will call the symplectic component the unique component of the restriction to SL, which is distinguished by the symplectic subgroup. Okay, so I should now be more careful. So over GL2n, all symplectic groups are the same, but they are not conjugate over SLN or SL2n. So the conjecture is about compatibility between these components, but for this compatibility, one has to choose the correct coordinates. So I guess for this statement, SPN is SP with respect to the following non-degenerate alternating form. So WN is the matrix with ones in the secondary diagonals and zeros everywhere else. And the conjecture of Stoll and Prasad is that for every pi irreducible, and SPN distinguished, the symplectic component is the Zelevinsky component. So the standard maximal unipotent orbit, the Zelevinsky one of pi, is actually also the maximal unipotent orbit of the symplectic distinguished component. So they proved the conjecture in a special case. So it holds for segment representations. And I generalized it to a class of representations that was introduced a few years ago by Lapid and Minguez. So this holds for ladder representations. And in particularly, this class contains what are called the generalized Speer representations. So these are the building blocks of the unitary dual of GLN. So I guess maybe instead of telling you what ladder representations are, since we're running out of time, let me just quickly explain how the proof goes for the case of segment representations. So the main tool that is also later used for ladder representations is what Dijol and Prasad called Clifford theory. Bernstein-Zelevinsky, which is basically, they very nicely put in a quite general framework ideas of Bernstein and Zelevinsky that came with restrictions to what is called the mirabolic subgroup of GLN, and they extended these ideas to other situations that in particular can be applied in this case of distinction for GLN and of GL2N and SP2N. So they put a nice general framework, and what the result it gives for our case is that if pi is a representation of SL2N that is SPN distinguished. Actually, they assume much less, so the result is much stronger, but that's the way I'm going to apply it. Then there exists some positive R such that pi is also, let me call it VR chi R distinguished, where VR is the following subgroup. And chi R of U1 H U2 and whatever you have above is the character theta R of U1 U2, so the generic character applied to each of these two blocks. So in other words, so remember, if we just focus on this block, equivalent linear form is the rth derivative of, amounts to looking at the rth derivative of pi. You can think of, so this is going to be a representation of this block. And now you're looking again at a subgroup of this form, but in kind of the opposite direction. The NR is now per left block instead of the lower right. So you kind of take a Bernstein-Zelevinsky derivative in the opposite direction. And you're saying that this representation is SP n minus R distinguished. But in fact, for Zelevinsky segment representations, the only rth derivative which is not zero is the highest derivative. So if you know that some rth derivative applied twice, one in the standard direction, once in the opposite direction, is SP distinguished. In particular, it's non-zero, so it has to be the highest derivative. And from there, it's easy to deduce by induction that you actually have a model for this representation with respect to the Zelevinsky period. So the main idea is the same for ladder representations, but the picture is somewhat more complicated. So I will finish with just saying in words what are the main two ingredients. So one is a computation derivatives of ladder representations, which was done by Lapid and Mendez, and applying their result. And the other requires some kind of compatibility condition for the conjecture with parabolic induction. And in order to do this, the Bernstein-Zelevinsky derivatives satisfy a Leibniz rule for GLN. And I had to verify that one can formulate an analog of this Leibniz rule for Bernstein-Zelevinsky derivatives in SLN. So one has to sort of think what this means and see that it goes through. Okay, so I think maybe I will end with a question. So all of this somehow indicates, and in many examples one can show it's true, so question, if pi is an SPN distinguished representation of GL2n, and I take the highest derivative of pi, and then take its highest derivative, is this also SP distinguished? And the answer is yes if the representation is ladder, and I have a suspicion that the answer should be yes in general, but I don't, since we don't, so this may be some tool that can help the classification in the future. I think I'll end here.
Could you just recall how you define derivative for SLN?
So, so in general, you can define a derivative with respect to a generic character. So the definition is exactly the same. You take the Jacquet module, with respect to this subgroup. And the only issue is that in general, not all generic characters are in the same orbit. So you want to somehow keep track of which generic character of NR are you taking. But so to fit with the Tijol-Prasad conjecture, I choose the standard one, because somehow the conjecture is coordinate dependent. And so one proves a Leibniz rule with respect to a general generic character. And then it translates very nicely in terms of the standard character.